Example 12 from 2.2. This is the last day of 2.2. An athlete swims from point A to point B at the rate of 2 miles per hour and runs from point B to point C at a rate of 8 miles per hour. Use the dimensions in the figure to write the time t required to reach point C as a function of x. Alright, so wait, want time t as a function of x. So they're looking for an equation that looks like this. T of x equals. So time as a function of x means t of x equals something about x over here. X is a unit of distance in this problem. Specifically, x is how far along the bank towards C that the swimmer is going to swim before he starts running. Okay, one option is to swim straight across the river and then run that distance. Okay, that's going to be more distance than doing this, but he's running faster than he's swimming, so maybe it's better to do that. You swim less, you run more, maybe that's faster. I don't know. We're not asked to solve the problem to figure out exactly where he should land on the bank. We're just trying to create a structure that represents this and how much time it takes. So, with the knowledge that rate times time equals distance, we're going to start there. I'm trying to get a time equation. So I know that distance, our time is equal to distance over rate. I'm going to start with that idea. So what I want to do to create this equation, t of x equals, is I need a swimming time and a running time. I have a swimming rate. He swims at a rate of 2 miles per hour. I have a running rate, runs at a rate of 8 miles per hour. So if I have the swimming rate and the running rate, I just have to have the swimming distance and the running distance in order to create a nice little time expression, right? So let's look at that. This is x. We don't know what that is. This is 1 mile. The river's not going to widen or shrink as the swimmer is swimming. That would be unfair to the swimmer. So the river is going to be a mile apart no matter where he goes there. The distance he actually swims, though, is right here. This is a right triangle, and the Pythagorean theorem states that x squared plus 1 squared is equal to d squared. Therefore, d of swimming is going to be the square root of x squared plus 1. Only the positive square root, because we're looking at a length there, it only makes sense to take the positive square root of that. So his swimming distance is the square root of x plus 1. So looking at this piece of it, swimming time, we know time equals distance over rate, right? So the swimming time is going to be the distance he swims, which is the square root of x plus 1, divided by the swimming rate, which is 2 miles per hour. Oh, sorry, x squared plus 1. So that's how you find t sub x. That's how long he'll be swimming. We go on to the running part. If he goes x miles along the bank here, how many miles are left right here?
3 minus x.
3 minus x. The entire distance from here to here is 3 miles. He's already gone x miles along the bank, so 3 minus x is left over. This is equal to his running distance, right? No Pythagorean theorem necessary there. That's just an actual distance given. So his running time is simply going to be his running distance of 3 minus x miles divided by his running rate of 8 miles per hour. Alright, so I've got this equation now. I got the time of swimming in terms of x, the time of running in terms of x, so the time in terms of x is simply going to be the swimming time of the square root of x squared plus 1 over 2, plus the time running, which is 3 minus x over 8. Alright, and that's the answer. Use the dimension in the figure to write time t required to reach point C as a function of x. T of x equals a bunch of stuff about x. We've made it all the way from A to B, the distance swimming plus the distance running, right? We've made it all the way to point C, so that represents what we're looking at. Now, what we can do with our calculator, again, we're not asked to do anything with this answer, but just to show you what we can do. If I were to type this in my calculator, the y value represents how much time it takes, right? There will be a spot where it dips down to the bottom, then it starts going back up, all right? That'll be the magical distance. That's the point he wants to hit. So we can actually figure this out. So if I type in the square root of x squared plus 1, I don't have to put that in parentheses, so the square root keeps it all as one object divided by 2, plus, and then I have to do 3 minus x in parentheses divided by 8. That right there, if I, obviously x is between 0 and 3, right? 0 means he doesn't go anywhere. 3 means he goes all the way over here, right? No running. All right. So if I make my window go from 0 to 3 on x, I don't know how long it'll take. If you were to swim the whole way, 2 miles an hour, the distance, so I could kind of figure it out. But let's just say that the minimum time it could be a 0, obviously more than 0. Let's say it might take 8 miles per hour, looks like about 4 miles. So maybe half an hour seems like, you know, let's just go 2 hours just to be safe if we get a number. And there's the graph. And notice that it dips down just slightly there, and then it goes up. So as x increases, the time increases. And x represents how far that bank is. So we need x to be a really tiny number. We can figure out that actual number there if I zoom in a little bit. Let's do a zoom box. I'm not going to zoom box. Go a different route. I'm just going to change my window. So I'm going to go from 0 to 0.5 on the x-axis. 0, 0.5. Let's go to 0.1 scale. I forgot to look at y, so let's just keep y like it was. Looks like it's under 1, right? So it hits the bottom right here, 0.1, 0.2, 0.3. Between 0.2 and 0.3, it's under 1 hour. So window, let's go from 0.2 to 0.3. Oh, 2, 0.3, go at 0.01. Let's go from 0.75 to 1. That'll give us more dip. Maybe not. Wow, doesn't give me any dip at all. 0.75 to 1, that's probably about maybe 0.85. Oh, you know what I can do? Let's trace it. 0.859. Let's go between 0.85 and 0.9 on the y-axis. I want to get more dip. 0.85, 0.9. Oh, it's dipping very slightly. I can at least see that now, right? So our window was, x was 0.2 by 0.1. So 0.21, 0.23, 0.24, 0.25, 0.26, 0.27. Somewhere in the 0.26, 0.27 range.
Change the y scale. You see
yeah, I changed the y some, but let's see. Don't want to change it so much I lose the graph. Let's go from 0.85.
No, the scale of it.
Oh, I see. 0.855. Let's go to 0.86 at a 0.001 scale. There we go. That's more like it. So 0.21, 22, 23, 24, 25, 26, right about the 0.26 range. It hits the very bottom. So that's kind of a way you can monkey around with that a little bit. Another way you can do it, if you go to calculate, this is actually more rapid, but calculate the minimum. It wants a left and a right bound, so I'm going to left bound at 0.2. So from 0.2 to 0.3, you got to be on screen. I'm going to guess 0.26. It gives me the exact minimum at 0.258 miles. About a quarter of a mile down. That'd be the perfect spot to hit to get the lowest time possible, and that lowest time possible was 0.859 hours. So less than an hour to do the whole thing. So your calculator can kind of work that through. There's calculus techniques to find the exact answer without the calculator. I mean, we can do some calculus to it, but not today because we're not calculus. But all we're looking for here is the function. So stop once you get the function. I just wanted to show you that there's stuff we can do with this function once we've created it. And that's kind of, this is a pre-calculus course, so that when we get to calculus, you can construct that equation pretty easily. then we can go do stuff to it. That's kind of where, what the stuff I did on the calculator was some ideas that calculus would find out, but again, not using calculus, using the calculator.